Okay, let's talk a little bit about controllers. Now, we can make controllers anything we want. Okay, it's only limited by our imagination, the type of controllers that we put in there. We can look at the system with the tools that we've been developing, and we can develop a controller that will accomplish what we want it to do. Okay, so anything is possible. Now, that being said, there are some industry standards, and these largely came out of the historic when controllers had to be created with hardware, resistors and capacitors and inductors. And so what they did was they created some standard controllers that could be configured with some variable resistors and variable capacitors, and so they could tune them and set them these standard controllers. Now this is continued to be a major part of the controller design suite, and it has come down to one of the major types, and the biggest and most common is a PID controller. Now we've been talking about this in class, we've been talking about it in the lab, but a PID controller is a controller, and it can be implemented in code. You can actually go out and buy a piece of hardware, a PID controller that has 3 little screws on it, and you can set those to vary your gains for your proportional, derivative, and integral. And so you can buy these, you can download the code for a PID controller. That code comes stock in many kind of devices. And so it is worth our while to understand PID controllers, and we've been leading up to this. And so one of the things that I want you to recognize in this is how we transition from the gain representation of it to a pole zero or pole zero gain representation, a transfer function kind of format. And so I prepared this for you, and let's take a look at it. Now, in the case of a proportional controller, there's no difference. The gain's the gain. We talk about the KP and we analyze it with the KP. There's no difference in the way we talk about it and implement it and the way that we analyze it. Now, when we move to a PD controller, okay, we talk about it in terms of KP and KD. Okay, you remember our motor lab, we set the gains, the KP, the KI, the KD in there. But how do we analyze that then? Well, you've seen this in the lab, but let me refresh your memory. We can simply factor out the KD out of our starting equation here and end up with a KD times S plus KP over KD. Now, this KP over KD we could call a Z, okay, a zero. And what we then end up with is a gain and a zero in here. Now, we can represent that in terms of our root locus or as in our Bode plot that is going to be coming up. And so we need to be able to move fluidly back and forth between the pole zero gain format and the gain format, okay, where we just enter the gains. And so this is the relationship between them. The KP over KD is the Z, okay, and in this case we factored out the KD, and our gain that we change is our derivative term. Okay, we can do a similar thing for the PI controller. Okay, we start out with our KP and our KI, and then if we factor or move them under a common denominator and factor out the KP, what we end up with is this equation here, KP, KI, S plus KI over KP divided by S. Okay, now again, this KP over or KI over KP we can think of as a Z, and what we end up with then is a gain, a zero, and a free integrator. Okay, now this is a little bit different than what we talk about because in the implementation of a PI controller, we actually pick up a free integrator and we pick up a zero. Okay, Okay, so we have both a pole at the origin and a zero that we can move around a little bit to change the performance of the system. And so this is the relationship between the gain format and a pole zero gain format for a PI controller. Now, a PID controller is a little more interesting, and we can go through the math on this, and I've actually put the math in here, and you can look at it at some later time. But this is the representation and relationship between for a PID controller. We've got gains. We've got a proportional gain, an integral gain, a derivative gain, all three having values. And in this case, what we're trying to achieve is to reduce the steady state error and speed the system up simultaneously. And so what we've got here, if we manipulate this, we end up with a gain, a couple of zeros in here, and a free integrator. So we've got these tools that we can move around in our S-plane to reshape the branches to achieve a performance that is acceptable or desirable to us. And so we can analyze it in this form. We typically implement it in this form. Okay, so it's a bit weird in there, but here's the relationship between the KI or KP, KD, KI, and the zeros, and it comes down to this relationship here. The KD. This is the KD is equal to KD, and that's a KD in there, and then a KI equal KP, KD Z1 Z2, and KP is equal to Z1 plus Z2. So we can go back and forth between those, analyze it in the transfer function form or the pole zero gain form, and then implement it in terms of KP, KI, and KD. Okay, so this is an important thing for you to understand because it's a bit cryptic at first what the relationship is between these gains and what we're talking about in class in terms of poles, zeros, and gains. And this is the tie that brings those two together.